All right, welcome back. This is still Chapter 3. We're going to do some two-dimensional kinematics problems. So here we go. A ball is thrown with an initial velocity of 10 meters per second at some angle above the horizontal on the top of a hill. What's the velocity of the ball when it hits the ground? Wow. So, first thing you want to do is read the problem twice. Think about it, visualize it. And then I'd recommend drawing a picture and draw your coordinate system and then label everything. And so we're going to do this pictorial representation. And you can see it's much more complicated than one dimensions, obviously because we have two dimensions now, right? Okay, so we're going to use a regular old good coordinate system. Plus top, plus right. Okay, here's the picture. So here's the ground. Here's the hill. You can barely see that. Now, this is where the ball is thrown. So it's at the top of the 40-meter hill. And I called this the origin. I didn't have to. I could have called this the origin. Doesn't matter. And so you can see that the velocity, initial velocity V0, is at an angle theta. Now, once it leaves the person's hand, the only force acting on it is gravity, so it's free fall. So that's that parabola. Okay, as far as the number of points, we want to know what the velocity of the ball is when it hits the ground. So all we really need are the initial points, and the initial point and the final point. But there's a lot of labeling because there's two dimensions. So x0, y0, of course t0. Now remember, we always want to split the velocity into the horizontal piece and the vertical piece. So v0x, v0y. And it's free fall, so the acceleration point's down. Our second point, x1, y1, t1, v1x, v1y. Now, I didn't bother drawing the motion diagram. You can if you want, but hopefully by this point in the semester, you don't really need to. So let's go. Okay, so first, we want to define everything here. And again, this is my origin. So if this is my origin, x0 equals y0 equals t0 equals 0. Now, we're giving that v0 as 10 meters per second. But again, we want the horizontal piece and the vertical piece. And the angle is 32 degrees. So v0x, v0 cosine theta, right? Cosine theta. v0 cosine theta, you plug it in, you get 8.5 meters per second. Now, remember, this is free fall. So v0x equals v1x, right? The horizontal velocities never change for free fall. So I said v0x, 8.5 meters per second, which equals v1x, which is constant because ax is 0. Now v0y, that's this piece. v0y, v0 sine theta. You plug it in, you get 5.3 meters per second. Also, you know it's free fall, so a sub y equals minus g. Okay, so let's see. We got everything here. Now here, we don't know what x1 is. We know that y1 is negative 40. Now why is it negative 40? Because we chose this to be the origin. We're using this as our coordinate system. So this down here, you know, the y, is negative. So it's negative 40. And if you forget that minus sign, the problem is wrong. We don't know t1y. Now remember, we want the velocity, right, when the ball hits the ground. So that means we want v1x and v1y. Well, we already know what v1x is, so that's nice. So all we have to really figure out is v1y. So I circle that just to tell my brain that's what I'm looking for, v1y. Okay, now you have to look at your kinematic equations. So let me find the kinematic equations. There they are. All right, so we don't know T1. So that's not going to help us. That's not going to help us. All we want is V1y. We know V initial y. We know delta y. So this is the appropriate equation. So V1y squared equals V0y squared minus 2gy. Now, what's y final? Y1 minus y0. Okay, let's get back to the picture.